Good morning, everyone. Today we're going to be going over our final project, which is on semi-supervised attributed network recovery. Project members are Xiao Wang, Qingchuan Song, Ying Zhang, and me, Henry Q. Just a brief breakdown, we're going to have an introduction, followed by literature review, objective, results, and conclusion. So many of you are probably familiar with a regular network, which is consisted of nodes as well as potentially weighted edges between them. Attributed networks differ in that every node has associated with it a set of attributes, or just free-form data. Also, these attributed networks may contain labels which are much more expensive and costlier than attributes. An example of this if we were to model Facebook, then nodes would be individual users, connections would be friendships, attributes would be the likes, comments, posts of these users, and the labels would be something like the university they attend, simply because you have to validate your email in order to be listed under that university. So it's much more expensive. As you can see, these attributed networks are powerful representations of real-world information systems. These include social networks, academic networks related to publishing, as well as healthcare systems. And however, in practice, these data sets are often incomplete and noisy. This is due to multiple factors, such as data collection errors due to privacy settings, API limitations, you can see in Twitter when we try to sample their fire hose, as well as inactive users, which produce far less data than the typical user. So, because this representation is used for many algorithms down the pipeline, it's crucial for us to be able to reconstruct any missing data that would otherwise skew or mislead the resulting models. Just for a brief literature review, attributed networks are widely studied. Here we have representing graph abstractions as subsets of vertices. There are other papers that use attributed networks to model content delivery networks as well as streaming media. Some other attempts at this data reconstruction are link prediction as well as matrix completion. And there are multiple ways to implement both of these classical problems. So the goal of our work is to be able to jointly reconstruct the missing data in all three aspects of the attributed network. So in network topology, in the attributes, as well as the labels. And this differs from the classical problems because they tend to typically just look at one problem in isolation. So the challenges that we faced were the incorporation of these heterogeneous data sources, meaning that both the representation and the meaning of these data sources are vastly different. And also, we attempt to tackle missing and noisy data in all three aspects, whereas most other methods rely on complete input data to predict missing data in the output, resulting in a chicken and egg problem for us. So our problem statement is given a set of attributes A, graph G, as well as a matrix of labels Y. We attempt to reconstruct any missing data in all three matrices. The main idea behind our method is inspired by a social theory called homophily, in which it boils down to simply similar entities oftentimes will come together and both connect with each other as well as share information with each other more often. So, because of this, we hypothesize that nodes with similar attributes and labels are more likely to be connected, and in order to take advantage of this, we seek to discover a latent matrix H that is instrumental in forming these attributes and labels. Here we see an example of what we mean. So given the previous example of A, G, and Y, we attempt to formulate the hidden representation H. For every node, we represent a vector. Every node is represented by a vector. And similarities between these vectors will correspond to similarities in all three aspects of the attributed network. So here's a brief overview of our model. It's a linear combination of 4 terms, the first 3 of which are representative of the topology, attributes, and labels, and lastly, we include a regularization term to limit overfitting. So the first term is responsible for the network topology. Here, we have the product between Sij, which is the similarity between nodes I and j, as well as the Frobenian norm of between Hi and Hj, or I and j, which is the distance in the embedded space. So by having the product of the two, as nodes are more similar, the distance between the two in the embedded space go down. And by minimizing this, we seek to just minimize the distances between the two. The second term is models are attributes. Here we have an attribute matrix A, which we then decompose into matrices H and V. Again, H is the same hidden representation matrix that we had earlier. So after decomposing A into H and V, we then alternatively iterate the updating of both A as well as H, similar to the EM algorithm that we went over in class. And then lastly, the third term of our model incorporates the labels. So here we use softmax, which takes in data and basically has a probability representation of that data. Typically, we would pick the class with the highest probability. However, because the rest of our terms rely on minimization, we multiply by -1, and meaning that minimizing this will result in the picking node I, which is most likely to be in class Y of I. So again, our final model is composed of 3 terms. We have the graph, we have the attribute, and then we also have the labels, and then the regularization term. So by minimizing this entire model, we come up with 3 variables: H, which is the hidden matrix; V, which is the transformation matrix used for finding the attributes; as well as W, which is a transformation matrix used for finding the labels. And in order to optimize this entire model, we use block coordinate gradient descent. For baselines, because we are the only model that incorporates all 3 of these tasks, we were forced to use 3 separate baselines, 1 for each classical problem. For link prediction, we use multispec. Matrix completion, we use low ramp, and node classification, we use LCMF. Our data sets are based off of 2 separate social media services. Blog catalog, in which it's an online community where users share and recommend blogs to each other. Attributes are keywords and blog descriptions, and labels are the categories that define user interests. And Flickr, which is a user and image sharing, which is an image and video sharing website, in which attributes are lists of tags the user is interested in, and labels are the groups that the users participated. As you can see in these are some of our results. As you can see, our results are typically outperform or are comparable in some cases to the classical ways to tackle the problem. And this is a ROC curve, which compares false positives to true positives. Typically, how to interpret these graphs is you want your classifier to be as close to the upper left as possible. Again, our result is comparable to other approaches, and in some cases outperforms them. And in conclusion, we developed a framework to jointly recover 3 aspects of an attributed network: the topology, the attributes, and the labels. And in addition, we learned a latent vector, which can then be used in a manner similar to word embeddings for future work. So you can have similarities, you can have antagonistic nodes, meaning just nodes that are very different from each other, so on and so forth. Are there any questions?
So how many data you can missing to predict those?
So, good point. So in here on this slide, the different percentages labeled up top, these correspond to different amounts of missing data. For example, so 10% through 50%. And then you can compare our results based off of, or our results against those of other methods, just to see how that influences accuracy rates.
And the missing data is which part? You have several, you have links, you have attributes, you have labels.
We have 10% of missing data in all three metrics: network, attributes, and labels, all random.
Whether can an example that have two missing, like I missed the attribute, I missed the label, and
maybe.
you're going to predict.
All
Just
is
using
random
the-
select, yes.
So I mean, we just assume the worst case scenario where you're missing 50% of all matrices. So if we had complete data in one matrix, it would perform better. All right, any other questions?
Do you have any explanation of the last raw result? Why the performance increases when you have more loss in data?
No, this is the error.
Okay.
The error increase.
Okay. Arrow increase. Yeah.
The,
Okay.
the first two is the accuracy. Second, the last row is for node attributes metrics recovery. The error minus the error between the ground truth and the predict one.
Okay.